that. Although I did give, going through the homework's taking longer than I expected. So I haven't finished it online. I don't know if anybody's been watching. Has anybody been watching those? Okay. Okay. Yeah. So I could move it to Thursday, if you want, but normally you're supposed to do, I don't know how many hours, 4 hours of homework, something like that per night. Chem. That's what people usually say, I think, or study 4 hours per day.
One per unit? One per unit?
Yeah, something like that. Actually, a lot. There's a certain number of hours that they have for that. So, since I'm still discussing the homework, I could push the exam to Thursday, or we can just have it tomorrow. If you guys want. Thursday? All right, Thursday. Although some of the latter ones are kind of complicated, the homework, so it's just more, you've seen, you have to do some different kinds of things to solve it. It's not necessarily actually sitting there and solving it, except for maybe simultaneous, you might want to know. That's what I'm talking about right now. Okay, so we'll just move it to Thursday then, and I'll finish up the homework tonight, I think. I'll do. Right, so I'll post it. I'm going to post the video today from yesterday. Although yesterday I did.
The two last ones,
those aren't going to be due for a bit. Because I need to talk about titration, and then I want to see what happens with the crystals. We'll see. But on the synthesis.
Define won't be due for a bit.
Okay. Do you want a hard deadline? I'll give you a hard deadline. Maybe we could have let's say a rough draft.
Yes.
A rough draft. How about a rough draft due next week? Is that good?
Next week, spring break.
Oh, next week. After spring break. How about that? Rough draft due after spring break. Okay. We can do that. Just turn in a rough draft and I can take a look at it and see,
And the titration lab.
And synthesis. Synthesis and titration lab, just start the rough, we already started a rough draft of the synthesis. The titration lab is going to be kind of similar. You have an abstract. The purpose was to identify an unknown acid. I assume everybody's already identified their acid. You identify the acid, and then you have to, support your identification with, observations, analysis, that kind of stuff. And so the bulk of the discussion for the titration lab will be trying to convince somebody that your identification is convincing, and supported by the evidence, scientific evidence. The nice thing about this is sometimes it isn't, sometimes things conflict, sometimes you have data, one supports, let's say, identification of one acid, like the Kas, for example, or pKas, and the other data, the mass supports something else, and then sometimes your equivalence points that you generate are, they're all supposed to be the same no matter what. The pH titration curve, the first derivative, the second derivative, the Grant's plot, all of them are supposed to give you the same equivalence point, did they? So these are things we talk about in the discussion section, because what you want is you want to talk about the limitations of, it's not like a black and white type of thing oftentimes, there's some things that, of course, if you had solid evidence, the molar mass matched exactly and the pKa's matched exactly, then it's very easy. But that's this is extremely rare. In fact, what's very common is you have, some evidence and you just, the example I tried to give earlier was Dalton. You know, did he have overwhelming evidence that atoms exist? No, and so it would be interesting to read his papers, you know, or his publications on why atoms. You know? And so it's kind of in the same vein that we're trying to do this. You know? And then the other thing is with the synthesis, you know, do we have overwhelming characterization evidence that, you know, these crystals are indeed the oxalato compound? No, so we have to use the same type of argument. But that's often the case because, you know, a lot of people think science, you know, in science you take on a project and then it's done. No, it's not really done. I mean, there's, you know, the next step. If I had to finish my project that I was working on for my PhD, I would still be there, you know, because it's not done. You're just doing certain, you know, contributing little steps here and there. You're not, you don't necessarily reinvent the wheel. If I had to reinvent the wheel, I'd have to go back in time, start from the beginning, you know, so you build up on what other people have done. This is why you do a literature search and you look for review papers and try to see what's already been done because they don't like to publish things that have already been done, you know, and so if you spend a lot of time doing research that people already know the answer to, it's not very productive. This is why, you know, people, the complete solutions manual to this book is available. You know, it's not, there are some errors in it, but it's out there. And the situation was when you do research, there is no solutions manual. There's no answer book. So you have to figure out, you know, is your answer correct? And how do you know it's correct? Well, you just present the best evidence that you can. And so this is how you're going to see, is your answer correct? Well, you're going to have to argue that to me, you know, or the reader, whatever that may be. Okay, so obviously everybody wants to know what was my acid, you know? That's not usually how it works. How it works is, you tell me what your acid was, that kind of thing. All right, so let's go on. Any other questions?
Is this chapter 16 library? Or?
Is this chapter 16?
Yeah, because
This is chapter 17. Oh, this is because I need the Ka values.
Oh, okay.
That's the only reason. Otherwise, well, I don't want to use the Ka values on this chart here because those are probably old. Or these Ka values on the book are probably more up to date. So last time we left off with a buffer. Chloride has no impact on the pH. And so this is what we call a Henderson-Hasselbalch buffer, an HH buffer. But any weak acid, weak base solution would be considered a buffer because they don't completely neutralize each other out. And it would be a stable solution of an acid and a base. But the advantage of a Henderson-Hasselbalch is the calculation is easy. When we have a weak acid, weak base buffer, that's not Henderson-Hasselbalch, that is, they're not conjugates of each other, we have to use simultaneous equilibrium to solve them. In fact, anything complicated, we have to use simultaneous equilibrium to solve it. And so this is the only thing, the reason why I wanted to go through some of the simultaneous in more detail in the homework, and that's why the homework is taking so much extra time. But looking at this, Henderson-Hasselbalch, you know, we can just get the pH is equal to pKa of the acid. So which one is the acid? H2PO4 minus or H3PO4? Yeah, H3PO4. So we'll need the pKa of H3PO4 plus the log of the base to acid ratio. So it's going to be the H2PO4 minus over the H3PO4. we can, if we ever forget this, you know, oftentimes it's easy to forget the Henderson-Hausbach. Is that supposed to be a plus or a minus? We can always figure out what's going to happen here. In this case, if it's base to acid, the more base we have, the bigger the log term becomes, and the higher the pH will have. The more acid we have, the smaller the log term will be, the lower the pH will be. And so that's usually the way I remember this. I mean, you can always derive it. All right, so I just grabbed the Ka, so we got to get the right Ka value. That's going to be the K1 here, for phosphoric acid. And so this is going to be the negative log of 7.1 times 10 to the minus 3. Okay, plus the log of the base, which is going to be 0.0015813, over the acid, which is going to be 0.0009982. Like that. So I'll just do this log term first. 0.015,813. Actually, you know, it's been so long since I've used this calculator. The log 0.0, I've been using my phone, 15813. The inputs is different. So they're messing up my calculations a lot. 15813. Someone have it?
About 1.3421.
1.3421 for the log term?
Oh,
1997.
1997. Okay. I got, did you get, did everybody get 1997?
Yes.
All right. I got 1998. Why did I get
Well, you round it to 9 after.
Yeah, 1997, 967.
Okay, I don't want this around. Okay, 1997. What's the next digit after that? 6. Okay. And then what was this? The TKE?
2.1487.
2.1487. Okay, and so this gives us a total pH of
2.3485.
and we're allowed 2 sig figs, so we'll go 2.35. And so what happened here was we overwhelmed the buffer, basically. And it went from pH 7 to pH 2.35, even though we end up with another buffer solution. But, you know, it's a different buffer. In this buffer system, the acid is much stronger than the base. And so the pH is lower. And so each buffer system will have a different, you know, idea. So if we use in other words, if we use the monohydrogen phosphate buffer system here, the optimum pH would be around 13, 12, 13. If we use the dihydrogen phosphate, monohydrogen phosphate buffer system, it would be around 8 or 7, the optimum pH, 7 to 8. This is close to 7, 6.3. Closer to 7 than it is to 8. And then if we use the phosphoric acid dihydrogen phosphate buffer system, then the optimum pH would be around, 2 to 3, basically, closer to 2. And so that's based on the Ka values there. And so here, although we do have what, 10 to the minus 3, 10 to the minus 4, 10 to the minus 3 for the base, 10 to the minus 4 for the acid. It's not terribly lopsided. And so this would be a buffer system. All right, let's take a look. That was buffers. And, you know, basically we handle all the problems in this chapter the same way. All the problems in this chapter are mixtures. And so the general method for solving these, there's the shortcuts I'm going to introduce later, but the general method that we can solve all the problems in this chapter are, if we have a mixture, then general method. When we have a mixture, what we do is we first do solution dilution. Then we get the strongest acid present plus the strongest base. And then repeat, basically, or just analyze what we have. So in this particular case, you know, for this last step, we did a shortcut. You know, we did a shortcut. We could have just done another ice table and taken the strongest base and the strongest acid present reactant, which would have been either Ka for phosphoric acid or Kb for dihydrogen phosphate. But, you know, when we look at both of those, they're redundant. That is, they both describe the same equilibrium. Just one describes it in terms of hydroxide, the other describes it in terms of hydronium. And so we could have just done Ka. But we saved ourselves this step by using the Henderson-Hasselbalch. So that was a shortcut, but we could have just kept repeating this. But there are other shortcuts that we can do as well to simplify things. So let's take a look at some other general problems here, chapter 17. So you guys are watching the videos then? Do you are those helpful?
Yes.
Okay, then I'll continue it for chapter 17 then. Homework as well. Okay. Let's just look at some of the sample combinations here. In example 16.4, we calculated the percent ionization of acetic acid in 1 molar, 0.1, and 0.01 molar acetic acid solutions. Recalculate those percent ionizations of each solution contains a common ion. Explain why the results are different from those of 16.4. So what's the common ion going to do? It's going to, it won't ionize. So the percent ionization is going to go down. You know, and so, well, here, this is not a typical chapter 17 problem. This is more of a chapter 16 problem. And we've done these types of problems before, where all we do is we start with this. I mean, the strongest acid present would be acetic acid, and the strongest base present would be acetate from sodium acetate. But sodium is a spectator. It's not going to do anything. So if we have acetic acid plus acetate, then we get NR, no reaction. And then we look, okay, what's better? You know, is acetic acid a better acid? Then acetate is a base. And so we just compare. And so, in other words, if I know the pKa of acetic acid, pKa of acetic acid is about 4. That means the pKb for acetate is, because they're conjugates. So if one's 4, the other must be 10. And so if this is 10, that's pretty weak. And so this is a much better acid than it is base. And so we would automatically go, okay, the strongest acid present would be acetic acid, we would go here. And then the strongest base present, other than acetate, would be water, because here we just get the same thing. Nothing changed. Okay. And so we go on here, and then what we realize is that this is going to form hydronium and acetate. And so we would have this
equilibrium where we're going to have the initial concentration of acetic acid plus the initial concentration of acetate and 0 hydronium. And so this is the common ion, starting point here with the initial. The more common ion we have, the more this Le Chatelier's kind of pushback occurs, and therefore the less ionization we will get. And so we could do that for different. Well, we saw in example 16.4, what you see is an increase in percent ionization as the concentration decreases.
I'm not going to go through the calculations. Some of these we will do.
Sure. Calculate the hydronium in a solution that is A, 0.035 molar in HCl and 0.075 molar in HOCl. So we have a hypochlorous acid solution. Hydrochloric is a strong acid, hypochlorous is weak acid. So normally in a solution like that, we attribute the pH. This is kind of like the common ion or the polyprotic acid. Step 1 is going to give the most hydronium unless step 2 has a significant K value. So let's take a look at the 2 different K values for these here. And so we start off, okay, we don't have to do solution dilution. It's already mixed for us. And so we're going to start off with the strongest acid present, which will be HCl, and the strongest base present, which will be H2O liquid. And this goes to completion, right, because Ka is very large. And so initial it might start off at 0.075 molar, but at equilibrium we'll have 0 molar HCl molecules. And then all the molecules will be dissociated into ions, and the ions are going to be, here 0.075 and 0.075. Now they're only interested in the hydronium or the pH. And so, chloride's not going to do anything here. Okay, now.
I'm sorry, is that the value for HCl or for?
For the other one, 35, sorry. 0.35. So we actually have more of the weak acid than the strong acid. And so what we do is, okay, so we have hydronium here. Are there any other contributors to hydronium? In an acid mixture, that's all we look for. In an acid mixture, we look for hydronium contributors. In a base mixture, we just look for hydroxide contributors. And so what else is going to contribute hydronium? HOCl. And so we'll take the next strongest acid and react it with the strongest base. And so we'll form some additional hydronium, which will change the pH, and hypochlorite HCl minus. So this is a common ion here. This is going to be 0.075 molar. So we have more weak acid than strong acid. So maybe it's going to be significant, but we're starting off with 0.035 molar here. And so that's significant initial hydronium, which is going to inhibit ionization of hypochlorous acid. And so here, it depends. So we're just going to do a quick calculation here. This is going to be minus x plus x plus x. And so at equilibrium, we'll have 0.075 minus x, 0.035 plus x, and x. All right, I'm just going to use this value because I'm not going to search it up in the book, but this value might be off a little bit from the book's value. We'll look up hypochlorous acid. And it's not there. So what I'm going to do is, I should have the chart. I should have put up the chart first.
Are we going to have access to the Ka and Kb charts?
Yes.
That's-
Yes.
okay.
Or I'll just put the Ka or the Kb value in the problem itself. So this table is 16.4 from our book. I'd like all the acids in the same chart. I don't like to split it up into two different charts.
Figure 16 in this table. No, it's not.
The Ka for hypochlorous is 2.9 times 10 to the negative 8.
All right, thanks. Oh, that's small.
But, you know, well, we might not have to worry about it so much because, you know, is it really going to be a significant contributor? Likely not. I mean, it's probably going to be negligible. So, but anyway, let's try it since we have it set up. 0.035 plus x times x divided by 0.075 minus x. And so this is going to be 0.035 times x divided by 0.075. So x is going to equal 2.9 times 10 to the minus 8, 2.9 times 10 to the minus 8 times 0.075 divided by 0.035. So x is equal to 6.2 times 10 to 6.2 actually, 21 times 10 to the minus 8. I usually carry at least one extra digit. In this case, I'm not going to carry all of them because it's going to be such a small. Actually, maybe I should. I'll carry all of them. 6.2143 times 10 to the minus 8. All right, was it justified? Which one's going to be a bigger percent change? 0.035 plus x or 0.075 minus x? Which one will be a bigger percent change? Yeah, so the percent change we should do is the bigger one. Because if it fails for the bigger one, then the bigger percent change is going to fail for the smaller percent change. And so this is 10 to the minus 8, that's 10 to the minus 2. So this is about 10 to the minus 8%, which is really good. I mean, the simplifying assumptions pretty much going to be no different than the quadratic. And so if the hydronium, well, actually, let's just make sure. 0.035 plus, I need 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then a 6, 2, 1, 4, 3. So did it change significantly? No. So this is going to be about 0.035. We'll just leave it. And this one definitely is not going to change significantly. This is going to be about 0.075. Roughly. I mean, it's going to be slightly less. But this one did change significantly. The hypochlorite definitely changed significantly. The hypochlorite is going to be 6.2143 times 10 to the minus 8. All right, so let's just double check our answer. So you take that times 0.035 divided by 0.075. And again, the K of 2.9 times 10 to the minus 8. So our K value is again 2.9 times 10 to the minus 8. And so it checks out 2.9000. All right, so what the point of this was is to show that, you know, if the K is small and we have a significant amount of common ion, we likely can skip this step. That's what this problem is showing. Now, when do we worry? When we worry about it is, you know, if K is big. K is big is like 10 to the minus 2 or something like that, then we worry about it. But there was a problem I did the other day where it was significant. Let me see if I can remember that problem. Oh, yeah. That's, you know, what we call a rule, a general rule of thumb. You
there are exceptions sometimes. But if you're pressed for time, then, that's a rule you could use, especially for multiple choice questions. Yeah, that's helpful. All right, so what were some of the other solutions that we had here? Okay, B is sodium nitrite with nitrous acid. Do you recognize the picture? HNO2 with NaNO2 is called a HH buffer. And so B, if you want to calculate the hydronium, I calculate the pH first. pH is going to be the pKa, which is the negative log of the K2, and plus the log of base acid. And so this is an HH buffer. C, what's that? Strong acid, weak acid.
Weak base, right?
Or, not an acid. This is a base, right? Sodium acetate's a base. Now, this one's a tricky problem because what's going to happen is strong acids always react to completion. And so you might not see this, but immediately what I see is which one's a limiting reagent? The acid or the base? The acid's the limiting reagent, so we're not going to have any strong acids left over because it's going to react immediately to completion. And it's a limiting reagent, so it's going to be gone. And so this is a typical problem here. We'll take the strongest acid being HCl, and then you're acting with the strongest base present. The strongest base present is going to be sodium acetate or acetate. It depends. We can leave it at sodium acetate. Sometimes people write the sodium at the end, because the negative charge is at the end here. And so sometimes you'll see this as CH3COONA. But whichever. Okay, this is just a double replacement or acid-base reaction. So it's going to form sodium chloride, I don't care too much about, and acetic acid. Normally, I like to do things just using the net ionic equation, because sodium acetate's a strong electrolyte, it splits apart, but then again, HCl is a strong electrolyte, so I'm not as strict with these. All right, so initial 0.0525. Sodium acetate is 0.0768. And sodium chloride 0 and acetic acid 0. Now K for this is equal to what? Well, it's more than very large. I call it very, very large. Because Ka for water, that's HCl plus water. Water is not very big base, is very large. And therefore, HCl plus a sodium acetate, which is much bigger base than water, should be bigger. All right, we figured out the limiting reagent. The limiting reagent is completely consumed. So this is minus 0.0525. This is minus 0.0525. So it's going to give us 3, 4, 2, 0. And this is going to be 0.0525. And this is going to be 0.0525. Plus. Then sodium chloride is not going to have any impact on the pH. And so we have our HH buffer here. And so it might not look like an HH buffer to begin with, but it turned into an HH buffer. And so this mixture is going to be very unstable. It's going to react immediately to form an HH buffer. And the HH buffer, this would just be the acetic acid, sodium acetate, or acetic acid acetate buffer. Here. All right, now we're looking at hydroxide in solution here. And so this first solution is going to be a strong base and its common ion here. Now, when we have a strong base, the strong bases have, do you know what a strong base is?
everybody has the strong acids memorized, the 7 common strong acids. There's more than 7, but what do we do about the strong bases? Do you have well, how many common strong bases are there? So 7? It'd be nice if there's that symmetry, but no, it's not 7.
It's less, right?
It's more.
Oh.
It's a lot more.
That's why you don't have a number, because there's so many of them. You know? Otherwise, you'd have but rather than memorizing each of them individually, we memorize them as a group.
And so what are the strong bases? The strong bases are the soluble amides. Well, what are soluble salts? This would be like the group 1 amides, or group 1 ammonium. Ammonium amide is not very stable, so we'll just say group 1 amides. Like sodium amide. An example would be sodium amide. Sodium amide, we don't treat as a strong base. We treat this as a soluble salt first, because all sodium salts are soluble. And so it breaks up into sodium ions and amide. And then amide we treat as a strong base. And what do strong bases do? Strong bases hydrolyze water. And so amide hydrolyzes water completely. Some people try to split amide apart, like we do for strong acids, like HCl. We could split HCl into H plus and Cl minus. And so they try to do that with amide, thinking it's a strong base. So I see all kinds of things for amide, nitrogen and hydrogen. And so this hydrolyzes water completely to form ammonia and hydroxide. The soluble amides, the soluble oxides, the soluble oxides would be the group 1 oxide. The soluble hydroxides. And others. And the others would be like more towards organic chemistry, where you have the things that are very much like a hydroxide, and others would be like methoxide ion. Methoxide is CH3O minus, where this is just like kind of hydroxide, except you replace the hydrogen with the methyl group. And then it would be just like hydroxide. And it'll be a strong base, just like hydroxide. And so barium, hydroxides are all insoluble except for group 1 ammonium and also strong in barium. So barium is a soluble hydroxide, therefore it's a strong base. Now strong bases, are they going to be perturbed by Lechazet's effect? And so, for example, here, this is a common ion problem. So I have barium hydroxide. This is going to go to barium ions and hydroxide ions. I'm going to have 2 hydroxides for every barium. And the barium hydroxide is going to be 0.0062 molar. And then we have some common ion here to begin with, 0.0105. And hydroxide, we're going to assume no hydroxide is yet formed. And so will this hinder the dissociation of barium hydroxide? In other words, will we have the common ion effect, which lowers the percent ionization? And the answer is no, because strong are one way. Strong are not affected by the common ion effect. So Kd is very large. It's a one-way reaction. And it's going to go to completion regardless if there's common ion or no common ion. I could dump in a whole bunch of hydroxide here. I'm just going to add to it, all of it. Versus weak. If this were a weak base, then yes.
that's going to decrease the percent ionization of this. Okay, so this is a common ion. The common ion, when K is large, has no effect. Le Chatelier's principle only works for weak species. I mean, K is not so large. All right, let's look at B. Do you recognize this? What kind of mixture is this? This is an HH buffer. We have ammonium and we have ammonia. So it's ammonium, ammonia. The trick to this one is for every ammonium sulfate, ammonium is going to dissociate into 2 ammoniums and 1 sulfate. We'll have to double this concentration for the HH buffer equation. That is, it's going to be 0.630, not 0.315, because we have twice as much ammonium as we do ammonium sulfate formulations. But the HH buffer. C, this is sodium hydroxide and ammonium chloride. Is that an HH buffer? Because ammonium's an acid, hydroxide's a base. Is this a buffer? This is not a buffer. This is a strong base, weak acid. The strong base, weak acid, we can figure it out. What's the limiting reagent here? The NaOH. The strong base is the limiting reagent. If the strong base is the limiting reagent, then we're not going to have any strong base in here, in the mixture, because it's going to be very reactive. And so what is that going to react to? And so we'll take the strongest base plus the strongest acid. The strongest acid present is going to be ammonium chloride or ammonia. You know, I don't care if you write this just and ignore the chloride. And sometimes it's easier. The problem, though, is this. The problem is what we do with the K equation. Let's say, you know, when we deal with K equations, I see this happen quite a lot. So people will do this. They'll have sodium hypochlorite. This hypochlorite's a base. Sodium is neutral. And they'll go plus water. And then what they're going to get is they're going to get sodium ions, hypochlorous acid, and hydroxide. And then they do the K equation for this. And when they do the K equation, they put in sodium ions, hypochlorous acid, and hydroxide divided by sodium hypochlorite. And they do all kinds of stuff like this, and then they end up getting the wrong answer because really the sodium ions are spectators. They don't even really belong there. It's hypochlorite plus water. This is a proper KB. And so they ended up calculating these and getting weird stuff. So when you write it, you know, you want to be careful. Like, oftentimes, you know, what I'll do is I'll just write it with just the ions and chloride spectator, sodium spectators. I'll ignore those, but in this case, we'll include those. This is not going to make any difference. And so we're going to get sodium chloride plus ammonia plus water. So liquid. Now K for this is very, very large because we have a strong base reacting with a weak acid. KB, when we have a strong base reacting with water, is very large. So this should be very, very large. And then we'll plug in the numbers here, 0.196. And ammonium chloride is going to be 0.264. This change is going to be complete, and so this is going to go down to 0. This is 264 minus 196. It should be, what is that, 8, 2, 1.
0.28 molar. This is going to be 0.196. 0.196. All right, so what do we have left over? You see what we have left over here? Well, what's the strongest acid left over? The strongest acid left over will be ammonium. What's the strongest base left over? Ammonia. So we have ammonium and ammonia. That's an HH buffer. We could react the two, but we're going to get no reaction. Ammonium plus ammonia yields ammonia plus ammonia. So we have an HH buffer. So, okay. Now what would happen if the strong base were in excess? Then what type of solution would we have? If the strong base were in excess, then we'd have some base left over, and we'd have no weak acid, and we'd have ammonia. So it would be a mixture of strong base and weak base. In a strong base, weak base mixture, the pH is predominantly going to be what is it? Well, it depends on the concentrations. The pH is going to be due to the sodium hydroxide mainly. And the weak base will be a very minor contributor. And so normally we just ignore the weak base. So we have some buffer solution problems which we looked at already. Well, this is continuing on trying to identify buffer solutions. And so, is A a buffer solution? No. This is neutral salt. pH should be 7. B. No, this isn't this weak acid solution. Sodium chloride, ignore that. It's not going to do anything here. And we treat the ammonium chloride as soluble salt, which is going to dissociate into ammonium chloride, ammonium solution. C. Yeah. This is the base. It's a methylamine. This is methyl ammonium chloride. D. You have to watch out because strong acids react to completion. So if this reacts to completion, what forms? Well, which one is limiting reagent? NaNO2. So do you know what I'm going to form here? I'm going to form a strong acid, weak acid solution. Do you see that? Here, I'll show you. And so when I look at that, it's not going to form an HH buffer. If the acid were limiting, then it would form an HH buffer, but the acid is in excess. And so we'll take the strongest acid, HCl, and react it with the strongest base, in this case sodium nitrite. And I'm going to form nitrous acid, HNO2, and sodium chloride. Yeah. And the HCl is 0.100, and the sodium nitrite is 0.050. And we're going to have a complete reaction. And so which one's the limiting reagent? It goes to 0. We're going to lose half of this. And we're going to gain the same amounts over here. And so I have a strong acid, weak acid mixture. This is chapter 16 style. We start off with the largest hydronium contributor, which will be HCl, and then work our way down. The next largest would be HNO2, and the next largest would be KW. And so In this case, HNO2 is pretty weak, so we might just ignore that. Just go with that. If we wanted to, we could determine it. We might not need that in this case. We can see what is HNO2's Ka. We should probably check that before we discredit it. So HNO2's Ka is 7.2 times 10 to the minus 4. If you look at these weak acids, the weak acids probably, some of the stronger weak acids, like 10 to the minus 1, 10 to the minus 2, I wouldn't ignore these. Because these stronger weak acids will probably contribute significantly. But 10 to the minus 3, I don't know. 10 to the minus 4, maybe. But when we get down here, 10 to the minus 8, 10, etc., probably wouldn't. And so let's just do this one just for experience. 7.2 times 10 to the minus 4. Will that contribute additional hydronium? Do this. And so we'll take the strongest acid. So we already did this step. We'll take the strongest acid and react it with the strongest base that remains. The strongest base that remains is just going to be water. Sodium chloride is neutral. So this is just Ka. And so this is going to go to completion. So we're going to be left with 0, and then 0.050 molar and 0.050 molar here. All right, do we stop here or do we look? Will HNO2 contribute additional hydronium? So HNO2 would be the strongest remaining acid other than water. And so let's see how much more hydronium we can generate. This. And so initial 0.050, and hydronium initial 0.050 from step 1, and nitrate nothing. Okay, this is going to be minus x plus x plus x. So we have 0.050 minus x, 0.050 plus x, and x. So Ka for this is going to equal 0.050 plus x times x divided by 0.050 minus x. We use a simplifying assumption here and we'll see if it works. So x is going to equal Ka, which is 7.2 times 10 to the minus 4. 7.2 times 10 to the minus 4, which gives us a percent change of x over 0.05 times 100. So what is that? 7.2 times 10 to the minus 4 divided by 0.05 times 100. 1.4. 1.4% change. That's getting kind of big, right? A little bit bigger. I might use the quadratic for this. In fact, we'll probably just do the quadratic. Even though this is acceptable, we can go with this. If it's a 1.4% change, I might factor that in here. Because, some people say, oh, 1% change, 2% change, no big deal. Ignore it, right? Other people will say 1% change, 2% change is significant. Can't ignore it. It depends on how accurate of a pH you want. If you just want the rough pH, then yeah, go ahead and ignore it, 1%. A huge difference in terms of pH, perhaps. But let's go ahead and I'm going to solve this using the quadratic to get a more accurate answer, I think. So 7.2 times 10 to the minus 4 times 0.05. 3.6 times 10 to the minus 5. minus 7.2 times 10 to the minus 4 x is equal to 0.050x plus x squared. And let's combine the terms here. So 0.05 plus 7.2 times 10 to the minus 4 would be, so I'm going to get x squared plus 0.05072 minus 3.6 times 10 to the minus 5 equal to 0. Okay, so just go to quadratic solver. Here, a is 1, b is 0.05072. C is negative 3.6 times 10 to the minus 5. And then an x equal to 7.0012 times 10 to the negative 4. So with the simplifying assumption, we got 7.2 times 10 to the minus 4. Without the simplifying assumption, we get 7.00. So we'll just use this. This will be more accurate. So let's see if it really made much of a difference. So this is going to equal 0.050 plus 0.0070012. So 0.0507012. So let's compare the two pHs. Well, actually, are they asking for the pH? If they're asking for the pH, is this a significant change or insignificant? Well, let's see what happens with the pH for this. And so we'll just do the first one here. Oh, actually, I'll do the second one here. I'm just going to take the log of that. 0.0507012. 1.295. So pH equals 1.295. What would the pH have been if I just stopped here and ignored this additional hydronium? So that's going to be log 0.05, 1.301. So if I stopped here, the pH would be 1.301 versus 1.295. 0.06 difference. It's not that much. Now, how many sig figs are we allowed in this? We're allowed 2 sig figs, so rounded, it'd be the same. So that's about. Now, it's going to become more significant. Let's say the acid were chlorous acid instead. Yeah, then it's going to be bigger than 1% additional hydronium, or iodic acid would be significant more. So it really depends on how accurate you want to be. But since we're limited by the sig fig, sometimes it makes no difference. All right, so we had a strong acid, weak acid. And so even though this started off as a strong acid, weak base, we end up with a strong acid, weak acid. Because remember, strong reacts to completion, so we got to do that first before figuring out what's left over. E, this is what?
Sorry, would it be considered a buffer solution?
Would D be considered a buffer solution?
No.
No. D is not a buffer solution because a buffer requires, okay, so what are we left over with here? So we're left over with 0 HCl. And then the hydronium comes down here. The chloride doesn't make any difference. And so what we're left over with here is a, let's do minus x here. This is going to be 0.049 to 0.0088. So we're going to be left with weak acid and nitrite here. But this is not considered a buffer because the only reason this is not considered a buffer, let me show, the nitrite is going to be 7.001 2 times 10 to the negative 4. This is not considered a buffer, although you might think it's a buffer because we have weak acid and its conjugate base. The difference between this solution and a buffer is this, 0. We added no nitrite in here to begin with, so this is not a mixture of weak acid. This is just hydrolysis. And we add a tiny bit of nitrite, which is not going to be significant. So in other words, this is just a Ka equation. Ka, which would just be acid and water, not a buffer because of this. And so this is the sole reason this is not a buffer. We started with 0 base. Started with 0 base, therefore not a buffer. Now, if we put in some base here to begin with, then for sure this would be a buffer. A buffer, you need both components and you have to mix them together. This is basically a chapter 16 problem. If that qualified as a buffer, then every single chapter 16 problem that we did with a weak acid, we'd have to consider that a buffer. So, for example, if we took acetic acid, 0.1 molar, we had 0.1 molar acetic acid, and this is 0.1 molar here, but there's no acetate. We need acetic acid and acetate. And over here, there's no acetate, so this is not considered a buffer. But when we do the hydrolysis, or the ice table, then we end up with acetate at the end. It's still not considered a buffer. Okay, so next one would be E, HCl and sodium acetate. Not a buffer? Well, it's not a buffer as is, but remember, strong acids react completion. So after that strong acid reacts, could it be a buffer? It depends on what the limiting reagent is. What's the limiting reagent here?
HCl.
HCl. So after this reacts, we're going to have no more strong acid left over. In its place, what are we going to have? We're going to have weak acid. And what's a weak acid? Well, so we have HCl plus sodium acetate. This is going to yield what? Sodium chloride, salt, and it's not salt and water, it's going to be salt and a weaker acid, which would be acetic acid. Now, we throw the H at the end here, we don't throw it at the beginning for acetic acid. And so this is limiting reagent. HCl is limiting reagent, which is 0.100. So we have 0.100, 0.200, 0, 0. And the limiting reagent is completely consumed. And so there should be none left over. And so we're going to lose all 100. And this is a 1-to-1 mole ratio. So it's minus 0.100. This is going to be plus 0.100 and plus 0.100. And so what are we left over with? We're left over with sodium acetate, acetic acid, which we call a HH buffer. In fact, I already know the pH. The pH is equal to pKa because this is a 1-to-1 ratio.
If sodium acetate was the limiting reagent, then would it not be an HH buffer?
It would not be an HH buffer. Well, it would be, if sodium acetate were the limiting reagent, we'd have strong acid, weak acid mixture left over. And so if we're interested in the pH is pretty much going to be dominated by strong acid. You know, the weak acid will contribute a little bit, but is it significant? Well, we have to make the call. If the K for the weak acid is very small, then definitely not. But if the K starts getting bigger and the concentration's big, then we start worrying about it a little bit. How about F? F, this is acetic acid, but this is sodium propanoate. Is that a buffer? Is this an HH buffer? This is not an HH buffer because it has to be acetic acid plus sodium acetate would be an HH buffer. But this would be a buffer. This buffer, we cannot use the HH equation for. It won't work because they aren't conjugates. They have to be conjugates one another. And so how the heck would I figure out the pH of this solution?
Like solve for the hydrogen.
F would have to be solved simultaneously. And so what would the simultaneous equilibrium be? This one would be a lot harder than the other ones because there's 3 equilibria that we need to solve simultaneously. The first equilibria is, this is 11F. The first equilibrium is the Ka. Actually, you know, I'd like to solve this like this. I'd like to solve this like, if I want to know the pH, I'd like to do it like this. Take the strongest acid plus the strongest base. The strongest base is going to be sodium propanoate. Propanoate is 3 carbons. So this would be the strongest base. So what would form from this? What's going to form from this is going to be sodium acetate and propanoic acid. The problem is this is not a strong. If this were a strong acid or a strong base, then this would react to completion. But what is K for this reaction? I don't know. And so there are some things you could do, like tricks you can do. Like, you know, what we can do is we can try to combine equations like with Hess's law. You know, if we combine equations with Hess's law, then that's fine. You could do that, you know, maybe this is a combination thing. That's one way. And so what we could do is we could take the Ka for acetic acid, take that equation, and take the Kb for sodium acetate, and then we would get it. And so it is equal to Ka for HAC times Kb for sodium propanoate. But there's a problem, and the problem is how are we going to calculate the pH? There's no hydronium, and there's no hydroxide to calculate the pH. And so from this equation, we're not going to get the pH. And number two is from this equation, it's not going to go to completion. We're going to have a mixture of these species present. And so what we can do is we can use any equilibrium that describes the equilibrium between the species. So the species is going to be acetic acid and acetate. What's an equilibrium that describes it, of the equilibrium between those two species would be Ka. And so if we did Ka like this, so instead of doing this, but the problem is no H3O plus to solve for it. So what we're going to do is we can go ahead and do the ice table for this, but what we're going to do is we're going to generate a whole bunch of species. Concentration of this, and this. Then what do we do? Well, then what we're going to have to do is we're going to have to figure out how much leftover acetic acid there is and do the equilibrium. And then figure out how much sodium propanoate there is and do the equilibrium, and figure out how much sodium acetate there is and then do the equilibrium. But fortunately, these two are described by the same equilibrium. Either the KD for this or the KA for this describes the exact same equilibrium, so we'll just do the KA. The KA for this is just going to give us hydronium plus acetate. So even if we spent some time doing this step, this is kind of a waste of time because we would just end up here anyway, and we just plug in the values here. The same thing goes for the sodium propanoate. And so let's do the propanoate, which we'll do over here. The propanoate is going to be CH3, CH2, COO minus plus water. This is going to give us propanoic acid plus hydroxide. Now, we could do these separately, you know, because they're unrelated, but it would be wrong. We'd get the wrong answer. Why? They seem to be unrelated. So can't we do two separate ice tables? You know, one with 0.100 molar acetic acid, and the other with 0.125 molar propanoate, and then solve that. Could we do that? But there's a reason we can't do it, unfortunately. You know what the reason is?
Are we not producing H3 alcohol?
We are producing H3O+. Yeah. The reason is because the hydronium and the hydroxide aren't independent of one another. If the hydronium goes up, what has to happen to the hydroxide? It has to go down, and vice versa. And so if we solve these independently, then the hydronium and the hydroxides need not match. They have to match, you know, that is, you know, they have to match according to Kw. And so these two equations are actually tied together. They're tied together by this. The hydronium and hydroxide are tied together. So we have three equilibria that we have to solve simultaneously. And so the setup would be more something like this. You know, we have some initial hydronium there from Kw. And so what we'll do is we'll call that Y. It's from Kw, and then we'll see 0 here. Kw. And so we'll generate some additional hydronium here, minus X, plus X, plus X. So we'll have 0.100 minus X. And this will be Y plus X. Right? This will be X. Over here, we'll have some addition. We'll have some initial hydroxide. The initial hydroxide is going to be from Kw. And so we'll call the initial hydroxide, should call that
Z.
Z. Okay, we'll call this Z. And so the change here is going to be, I'm not going to use X here. I'm going to use, I call this from Kw, so I need more letters. F. All right. Minus
I
F.
already reached the end of the alphabet, so where do we go?
That's that. equilibrium, I'm gonna have 0.125 minus F. F, because it starts off at 0, and Z plus F. All right, and so then we go to Kw. For Kw, I'm going to have hydronium here from X. That is, this is going to be the hydronium from Ka. And the change here is going to be plus Y, we saw. And then at equilibrium, we make X plus Y here. And then the hydroxide, I'm going to have F. And then this is going to be plus Z. And so I'm going to get F plus Z. Okay. And so the two hydroxides have to match here. And the two hydroniums have to match here. And then it's all consistent. You know, it's balanced, right? And so how do you solve this?
Okay, so you can do two tables, but then you have to end up matching them up.
Yeah, everything has to match up at the end. And so how do you solve this? How you solve this is system of equations. We solve this using system of equations. System of equations isn't too bad, you know, when we don't have too many things. But this starts to get bad. And we start having a lot going on.
We haven't gone over any simultaneous in class. We think go over a simultaneous equation, or are we not going to have to do that for an exam?
For an exam, simultaneous, you have to be able to recognize simultaneous. It's simultaneous, and that needs to be solved by simultaneous methods.
So can we go over something in class that's simultaneous?
We did a couple of ones. We did the
Actually, I mean, the last time you did one, you just went, oh, I'm not going to do that. And
Right.
We skipped it.
no. The last thing we did was you have to recognize it and say this must be solved by simultaneous means because step 2 for sure step 1.
And that's it, right?
And that's it. That's full credit.
So you don't
But-
have to actually solve these.
No, I just said if you solve it, that's strictly bonus. If you, and there are people who like math or want to do the math, that'll solve it. You know?
Okay, so we just need to do it to recognize it.
Right, that would be full credit, right? But extra credit would be to actually solve it, which is what I've been doing. So it's not necessary to do. Therefore, I skip it in class. I don't think everybody wants to learn how to do simultaneous.
I was just worried we're going to actually have to solve something like this because I have no idea where to even start.
Yeah.
The book is like, use computer, like, use a computer thing for it. It's like, okay.
Well, that's why the example I did in the Zoom was from the book because the book skips some steps there. So I didn't skip any steps in the simultaneous. Where is simultaneous? Be at the end of the section. Well, anyway, a couple of things. One, if you haven't been attending the Zoom sessions, so the book does skip some steps, but I went through it step by step. And then the way the book did it. But the system of equations, which is a different method, the way I did it was 2 equations, 2 unknowns, which is a system of equations. But there's another way of doing it, and the other way of doing it is by mass balance and charge balance. If you have the answer, the solutions guide, the answer in the solutions guide is wrong for problem number 89. You can't do it that way. It doesn't work. And so I went through the mass balance and charge balance, 89A. Then I was doing 89B last night, but I got mixed up with something. It turned out to be something very simple. Just missed it. I'll do it again. No. But that's the extra. And so it's for people who want. Sometimes the advanced problems aren't so advanced, you know. So those problems are reasonable. Sometimes the advanced problems are pretty hard. So we're running out of time here for today, but what we're going to do is we're going to do titrations next. And so titrations follow the same thing, except we're going to have to do solution. And there are lots of shortcuts that you can use for titrations. So let me jump to from buffers to titrations. Buffers are what you've seen in titration problems for weak species. And so when we have a titration problem, note the difference here. 25 milliliters of 0.16 added to, 10 milliliters and 15 milliliters of 0.242. So this is automatically solution dilution. So whenever we're mixing solutions together, we have to do that. But otherwise, it's going to be very similar to what we've already done in the first part. That is, here, what's a limiting reagent? Is a strong acid limiting reagent? The strong acid limiting reagent, we're adding it to weak base. We might form a buffer, but in this case, we have a strong acid and a strong base. And so we're just going to have excess acid. And so we just look at the solutions that are left over. If we can't tell what the solution is, then we'll just do the equation. So here, it depends. What's the limiting reagent? What's the excess reagent? If it's stoichiometric, we're just left with the salt. And so we just generate an ice table and then figure it out. And so titration problems are very similar to what we've been doing. In fact, they're just more of the same. In fact, the calculations that we just did are the exact same ones we're going to do in titrations. And so it's just more those types of things. So we'll be looking at that next time. So we're out of time.